Quantum computers. The rise of the machines beyond imagination. In the shadowy frontier between science fiction and tomorrow's reality, a revolutionary technology is taking shape, one that promises to redefine what we understand as computing. Welcome to the world of quantum computers, where the rules of classical logic collapse under the strange and powerful laws of quantum mechanics. Here, machines perform calculations once thought to be impossible, shattering records and turning even the mightiest of today's supercomputers into quaint relics of the past. And now, from the cutting-edge laboratories of China, a new challenger emerges. The Zhuchongji 3.0 quantum computer. Named after the legendary Chinese mathematician and astronomer of the 5th century, this machine isn't just a marvel of modern science. It's a herald of the next computational era. A giant leap. The birth of Zhuchongji 3.0. Developed by a team of Chinese researchers under the leadership of Jianwei Pan, one of the world's foremost quantum physicists, the Zhuchongji 3.0 quantum computer is the latest in a series of advancements in China's growing quantum technology program. Like its American counterpart, Google's Willow quantum processor Zhuchongji 3.0 operates using superconducting qubits, the fundamental units of quantum information. But what does that actually mean? And why is the world watching? Let's step back and understand what makes quantum computers so radically different from the devices we use today. From bits to qubits, a new logic of computation. Today's computers, from smartphones to data centers, all rely on a digital system based on binary bits. A bit can only be in one of two possible states, 0 or 1. At any given moment, each transistor in your device is either on or off, encoding data in a strict linear sequence. It's reliable and fast, but limited. Quantum computers, on the other hand, use quantum bits or qubits, which are governed by the laws of quantum mechanics. Unlike classical bits, a qubit can exist not just in the state 0 or 1, but in any superposition of both at the same time. Imagine a coin spinning in the air, not just showing heads or tails, but an infinite blur of possibilities. And here's where it gets really powerful. When multiple qubits are entangled, a unique quantum phenomenon, their states become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This gives quantum computers the uncanny ability to explore a vast number of solutions simultaneously. Let's put that into perspective. 3 qubits can represent 8 different states at once. 10 qubits can represent 24 states. 300 qubits can represent more possible states than there are atoms in the observable universe, a number so large it's practically beyond comprehension. This exponential scaling of power means that quantum computers, in theory, could solve problems that would take classical supercomputers billions or even trillions of years. Unthinkable speed. 6.4 billion years versus a few minutes. The Chinese research team recently announced a result that stunned the scientific community. Using Zhuchongji 3.0, they completed a computational task in just a few hundred seconds, a task that would take Frontier, the world's most powerful classical supercomputer, over 6.4 billion years to complete. Let that sink in. That's half the age of the universe, compressed into mere minutes. This milestone was achieved through a test known as random circuit sampling, a complex process that pushes quantum systems to their limits by applying a series of randomized quantum gates to entangle qubits into highly complex configurations. Classical computers choke on this task because the number of possible quantum states grows too fast to simulate. But quantum computers thrive in this chaos. And Zhuchongji 3.0 isn't the only machine flexing its computational muscle. The quantum race. Zhuchongji 3.0 versus Google's Willow. Across the Pacific, Google's Willow quantum chip has been setting its own records. Built on 105 superconducting qubits, just like its Chinese counterpart, Willow recently made headlines by achieving a breakthrough in quantum error correction. Why is this important? Because as powerful as quantum computers are, they are also incredibly fragile. Qubits are easily disrupted by tiny environmental changes, vibrations, electromagnetic fields, even cosmic rays. These tiny disturbances can cause the system to decohere and lose information, making long or complex calculations unreliable. Google tackled this issue with a method called the surface code. Instead of storing information in a single qubit, data is spread across multiple physical qubits to form a logical qubit. This redundancy allows the system to detect and correct errors without destroying the delicate quantum state. In its latest test, Willow managed to double the number of qubits without increasing the error rate. In fact, it halved it. Its qubits maintain superpositions 5 times longer than those in Google's earlier Sycamore processor. This is a huge step forward, laying the foundation for scalable, practical quantum systems. While Google focuses on reducing errors for long-term utility, the Chinese team emphasized scaling performance, handling exponentially more difficult tasks, with unprecedented fidelity rates exceeding 99%. 2 different approaches, both critical, and the race is far from over. When will quantum computers impact our daily lives? With all this incredible power, you might wonder, why isn't there a quantum computer on your desk right now? The short answer is, we're not there yet. Quantum computers, today, are still in their infancy. They're delicate machines, requiring temperatures close to absolute zero, minus 273.15 degrees Celsius, to function. They must be isolated from any external noise. Operating them requires cryogenic systems, vacuum chambers, and highly specialized equipment. Currently, they're used in controlled environments, labs, universities, and government facilities, not in everyday life. They're powerful, yes, but still specialized tools. That said, the future holds immense possibilities. What will quantum computers be good for? Despite their current limitations, the potential applications of quantum computers are breathtaking. Drug discovery. By simulating molecules at the quantum level, researchers could identify effective new medicines in days, not years. Entire clinical pipelines could be revolutionized. Artificial intelligence. Machine learning models could be trained exponentially faster, learning to process and interpret complex data in ways that today's AI systems can't even begin to comprehend. Cryptography. Most of today's encryption relies on problems that are hard for classical computers, like factoring large numbers. Quantum computers could crack these codes easily, prompting the need for post-quantum encryption. Climate modeling. Simulating the Earth's atmosphere with greater precision could lead to better predictions and more effective strategies for tackling climate change. Material science. From ultra-efficient batteries to superconductors and carbon-capturing compounds, new materials could be engineered atom by atom. And these are just the applications we can foresee. Just as no one in the 1940s could imagine smartphones or streaming video, we likely can't even dream of all the use cases quantum computing will enable. A glimpse into the quantum future. We are witnessing the birth of a transformative technology, one that will reshape entire industries, scientific research, and even our understanding of reality itself, The competition between nations and tech giants is heating up, pushing boundaries faster than ever before. Today, quantum computers, like Zhuangzi 3.0 and Google's Willow, are making headlines. Tomorrow, they may be curing diseases, designing artificial life, or simulating the universe from its first moments after the Big Bang. So while your personal smartphone won't be quantum-powered anytime soon, the ripples of quantum computing will soon touch every corner of our lives. From the smallest molecule to the vastness of the cosmos, the quantum revolution has begun.